So we've been talking about graphing quadratics, and last time we had met we talked about finding the vertex, which was an important part of being able to graph a quadratic. So the parent function for quadratics is y equals x squared, and the graph for y equals x squared looks like this. What was the name that we called this kind of shape of graph? Parabola. Yep. On a parabola, there's 5 key points that we want to worry about. So they are 2, 4, 1, 1, 0, 0, negative 1, 1, negative 2, 4. Now, in the previous chapter, to graph a function, we had used our transformation of a parent function idea, right? We did the transformation maps. So what I mean there is we used this information to transform the key points on the parent function into points in the graph that we're trying to graph. Now, this is really convenient if we're dealing with a quadratic that's in vertex form, because it's easy to identify the A, H, and K here. If we're in one of the other forms, it's not nearly so easy as to identify the A, H, and K, and we're not going to use this process in anything other than when we're in vertex form. So let me just show you guys an example. So let's say we have this vertex form equation. Everybody can identify this as vertex form. So what is the value for A, H, and K here? Very good. Very good. Very good. Everybody happy with how we did that? So I'm going to write my transformation map. So remember that's x plus h, ay plus k. And I'm going to just do that to my 5 key points. So if I have an equation in vertex form, it's just like what we've been doing for the last 2 chapters. Nothing unusual or different or anything else is happening here. We're doing the exact same thing that we've been doing. Any questions about how I was able to generate those points there? Again, all I did was I took my x-coordinate and I plugged it in place of x. So negative 2 minus 3 is negative 5. Similarly, I did the same thing for my y-coordinate. So plugged 4 in for y. So negative 2 times 4 is negative 8. And then minus 5 more is negative 13. And I did that for each point to get the answer. So what I'll do now is I'll graph this. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 at the very bottom there. So negative 5, negative 13. -4, -7, negative 3, negative 5, negative 1, negative 7, oops, that's negative 2, negative 7, excuse me, and then negative 1, negative 13. So we're going to look like this. Everybody okay with that idea? So this should look very familiar, right? This is exactly what we've been doing the previous 2 chapters. Grace? You're welcome. So if I have an equation that I'm graphing that's in vertex form, really nothing is going to change. I'm going to approach this the same way I have each time before. The catch is, what am I going to do if I'm not in vertex form? Because there's not an easy way to identify the A, H, and K if I have my equation in standard form or in intercept form. So let's talk about what to do in those situations. What we're going to do is we're going to make a 5-point XY table. The vertex is the middle point in that table. And then we're going to choose 2 points on either side of the vertex. So that's the idea. Because we don't know how to find the A, H, and K, which we'll talk about how we can do that, but it's the process for doing it is not a lot of fun. And this is the process that I'm describing here is actually, in practical terms, a much simpler way of doing that. So let's look at an example. So let's look at this example. Now I've said this is an intercept form. Does this look funny to you guys? Why does it look funny if I'm saying this is an intercept form? It feels like there should be 2 sets of parentheses and you only see 1, right? So what's going on here is that because that second set of parentheses is missing, that first x, we must have just been subtracting 0 from it, right? We see that if I wrote with what I've written in red, if we simplified this, we'd get to the same thing I had in black. Everybody agree with that? So looking at this, you can now definitely tell that, okay, sure, because I can write the equation in black the same as I would write this equation in red. Certainly the red one is in intercept form, so the black one must be as well. Does everybody agree with that? Okay. So what is my P and Q in this situation? P is 0 and Q is -4. So again, the general form for intercept is A times x minus P times x minus Q. And remember, the P and Q are kind of the opposite signs of what they appear in our function. So the outline that I've described before, or above, says that we need to make a 5-point XY table with the vertex as the center point, or the middle point in our table. So let's find the vertex here as our first order of business. So I know for intercept form, the formula for the x-coordinate of the vertex is P plus Q over 2. So that's -2. And the y-coordinate of the vertex, I'm just going to plug -2 in for the x's. It doesn't matter which of the two equations you plug the -2 in, the red one or the black one. I plugged it into the black one because it's already a little bit more simplified, but there would be nothing wrong with plugging that into the red one either. You get the same result. So this is -2 times -2 times +2, which is equal to 8. So I'm going to write now a 5-point XY table. I chose to write mine horizontally. I think it's just more space efficient for me to do it that way. That's the way I like to write my XY tables. You can write yours vertically, though, if you prefer. So you'll go and see that I've written this XY table. There's 5 spaces in it. I've already went ahead and wrote the vertex in the middle spot. I put a big V over top of it, so I remember when I look at my notes that was the vertex. Everybody okay with what I've done to here? So the next part says to choose 2 points on either side of the vertex. So to do that, I'm just going to choose x values. So I'm going to choose 2 x values that are larger than the x-coordinate of the vertex, and 2 values that are smaller than the x-coordinate of the vertex. It doesn't really matter which ones I choose, so I'm going to just choose them conveniently. So to me, it seems like it would make most sense to do -4 and -3 on the left side, and -1 and +0, well, not +0, and just 0 on the right side. So my 5 x-coordinates are -1, or -4, -3, -2, -1, and 0. So they just go right in a line like that, nice and easy. Everybody okay with how I chose those x's? Just try to pick them conveniently, right? Whatever seems to be the most convenient. And now what I'm going to do to find the corresponding y-coordinates are going to be the same thing I did when I found the y-coordinate of the vertex. I'm just going to plug these y or x-coordinates into my function. To find the y value. So when I plug in -4 in for x, I have -2 times -4 times -4 plus 4. Are we okay with where I've gotten these numbers from? So what I did is I plugged in -4 into the x's of my original function, right? Everybody see that? And obviously -4 plus 4 is 0, and anything times 0 is 0. So I got a 0 there. So I'll write that in my table as my y-coordinate. Now I'll do the same thing for -3. That gives me 6. And then I'll do the same thing for -1. And that also gives me 6. And then once more doing it for 0. And that gives me 0. So a little bit more time consuming than having to use the transformation math, but not terribly so. And I want to point out to you, notice that this XY table looks symmetric. So if I look, I have a y-coordinate of 6 on either side of the vertex, and then 2 spots from the vertex, the x-coordinate or the y-coordinate of 0. Yes, sir?
Will those ever, like, will those 5 points ever change? Like, if it's 0 and 0 and -1 and 0, will they sometimes be 2 different numbers, or will they always be the same number?
So, what I want to keep trying to call you Ryan, and it's not your name. Tell me your first name. Nicholas, thank you. What Nicholas is asking is, we observe we have this kind of symmetry going on here. What he's asking is it possible that, say, the y-coordinates here at the ends, would those ever not match? Would there be a situation that, would these y-coordinates possibly not match? Like we're seeing them match right now. And that's what you're asking, correct? The answer is yes, but not if you choose your x-coordinates carefully. So remember we had a choice for picking our x's, right? Everybody remember that? So if you notice, all of our x-coordinates are just increasing by 1 unit. Everybody see that? As long as that increase is constant, you're going to have this symmetry that we pointed out. If, say, I picked this last one to go up by 2, and that number was now a 1, we would not get 0 at the end, and we'd ruin the symmetry in our table. So if you pick your x's symmetrically, so they're like evenly spaced out, you'll get the y's to match up like we're seeing them match up here. If you didn't, then they won't. And there are times where it's more convenient to pick your x's so that they don't match. And we'll look at an example here in a moment where that's the case. Elena? So I had this one as my middle, and I would prefer to deal with whole numbers rather than fractions. So I just picked the nearest whole numbers to -2. So the closest ones left of it were -3 and -4, and the closest ones to the right of it were -1 and 0. Nothing trickier than that. So I chose them purely for convenience, and it has a double convenience. Not only are those whole numbers easy to calculate or do calculation with, I also get this nice symmetry effect with my y-coordinates that makes it easy to kind of check to make sure I haven't done anything wrong. And the thing that would be the most likely mistake you would make, that would cause the biggest problems long term, is goofing the signs on your P and Q. If you do that, you'll lose the symmetry in your table and have a really good indicator that you've made a mistake somewhere in there. You're welcome. So Nicholas had asked, is there ever a situation where the y-coordinates wouldn't match up? And basically we said, not if you choose your x's in a certain way, right? let's look at a situation where maybe we wouldn't want to pick our x's in that convenient way. Okay, so this equation is standard form. Can everybody see that it is standard form? So the first thing that we need to do if we want to graph this standard form equation is to find the vertex. So I remember to find the x-coordinate of the vertex in standard form, I need to do negative b over 2a. My value for b is 5, and my value for a is 2. So this is negative 2 over 2 times 2, or negative 5/4. Everybody okay with what I've done there? To find the y-coordinate now, I'm going to plug that value for x back into the original function. So, now I'm just going to simplify. So, negative 5 over 4 squared. To do that, I can just square the numerator and square the denominator. And then to multiply fractions, I'm going to multiply the numerators together and the denominators together. So negative 5 times 5 is negative 25, and 1 times 4 is 4. So that plus 1 there. So far, so good. So now I need to multiply these two fractions together. What I'm going to do is reduce first and then multiply. So I notice that the 2 and the 16 can reduce down. And I'm left with these three fractions. I'm going to actually write 1 as 1 over 1 and kind of cut to the chase here. So to add these three fractions together, they need to have a common denominator. That common denominator in this case should be 8. So 25 over 4, I'm going to multiply by 2 over 2. And 1 over 1, I'm going to multiply by 8 over 8. And when I do that, I have 25 over 8 minus 50 over 8 plus 8 over 8, which comes out to be negative 17 over 8. Goodness gracious, it took me too long to do that mental math. Everybody okay to there? So my vertex is the very nasty looking negative 5/4, comma negative 17/8. Since we're going to be graphing this, I'm going to convert these into decimals, because I don't know about you, but figuring out where 17/8 is on the xy axis is not super intuitive. But I could just do that division on my calculator or something to get a decimal approximation. Is everybody okay to hear? So now let's make our xy table. Thank you. So I'm going to make how many spots on my xy table? 5. And what goes in the middle? The vertex. And again, just for notes purposes, I'm going to write a big V over top of that spot, so I remember how I built this table is I started with the vertex in the middle. Now, if we're going to choose our x-coordinates, what would you want to choose for the left-hand side? Okay. And what else? Good. That's fine. And for the right-hand side, how about -1? Right? And then 0. You could pick positive too. There's nothing wrong with that. You're probably going to get you'd likely get a number that's a little bit difficult to work with, like something really, really big. So the closer we can kind of pick them to the vertex, usually the better off we are. But 2 would not be a wrong answer. It would just be kind of inconvenient. Everybody okay with picking these? And hopefully these would be the obvious x's to pick, right? These are the whole number x's that are the closest to -1.25. Everybody agree with that? Now, am I going to get a symmetric set of answers here for my y's? No. Notice here we go up by 1. Here we go up by 0.25, or 0.75, excuse me. Here we go up by 0.25, and here we go up by 1. So I would not expect my y coordinates to match up symmetrically, but I wouldn't really want to pick decimals and fractions for all these x coordinates, which would be the option to make the y's match up, is I'd have to pick a decimal or fraction for all of these x's, which seems like more work than plugging an extra 2 points in to get that symmetry. So Nick, this is a situation where I wouldn't expect it to happen, and I wouldn't even try to make it happen, because I think it's more trouble than it's worth. Does that make sense? Does everybody else kind of follow what I'm describing here? So I'm going to pick my x's to be convenient. On occasion, that means that maybe I don't get the y symmetry that I hope for, but I think it's a fair trade-off rather than dealing with a bunch of extra decimals or fractions. So my goal is usually to try to find a way that makes my life easier, and this is certainly a situation where being careful with how I'm picking my x's can make my life a little bit easier. Okay. So I think I had 2x squared plus 5x plus, I forget what the end was. I picked 1. Okay. Sorry about that. So -3 squared is 9. 2 times 9 is 18. -3 times 5 is -15. Plus 1 is 4. And then plugging in -2. -2 squared is 4. 2 times 4 is 8. 5 times -2 is -10. And then plus 1 is -1. Plugging in -1. -1 squared is 1. 2 times 1 is 2. 5 times -1 is -5. And then plus 1 is -2. So notice that we're not getting that symmetry on the y's that we had earlier. But that's okay. We kind of expected that to happen because we know that we chose our x's in a way that wasn't symmetric. They weren't all equal distant apart. Is everybody okay with that? So these other two situations are a little bit more calculation intensive. We have to do a little bit more than just using our transformation map, which is a shame. And a little bit later this chapter we'll talk about how we can change the forms to go from like standard form into vertex form. It's not convenient to do. It's actually, algebraically, it's quite a bit of symbol pushing. So it's not super easy to do that, or else I would have suggested we do that. We'd start by doing something different so that we can take advantage of that to do this graphing. But it's not super convenient. I think this is actually a little bit less work. So that's why we're starting going in this fashion. Okay, so one last thing to talk about in regard to graphing. It's domain and ranges. The domain is easy. It's always negative infinity to positive. What is that the same as? Absolute value functions, right? We're also had all the same domain, and this was their domain as well. That's convenient. The range has two cases. If the A value is positive, we're going to go bracket the y coordinate of the vertex, comma, positive infinity. If the A value is negative, it's going to be negative infinity to the y coordinate of the vertex with a bracket. What does this look similar to? It looks a lot like the range for the absolute value functions we just talked about, right? We had the same kind of thing. And notice that in this situation, if we're dealing with vertex form, what is the y coordinate of the vertex in vertex form? It's k, isn't it? And now it is exactly the same rule for range as for absolute values, wasn't it? It's exactly the same rule. That's convenient.